Hello, this is Doug Sweetser, and this is a talk I have been preparing for the Midwest Relativity meeting on October 24-25 at Notre Dame University. The first half of the talk is devoted to my unified field theory, going through the logic behind that, and then the second half is devoted to the vector coupling problem with that proposal and kind of trying to work through that issue. When we were young, we all accepted the unification of gravity and electromagnetism. The first important law we learned is Newton's law for gravity. So powerful, it described how the Earth goes around the sun, moon goes around the Earth, and it's very simple. It's amazing that such a simple expression governs such large bodies. When we start to learn about electromagnetism, the first law we learn is Coulomb's law. And it has a very similar kinds of features to it. If we be more precise by what we mean, we notice that we have different players at exactly the same positions. So you have two different types of constants, and you have two different types of charges, mass and electric charge. You have an r squared term, and you have an r hat direction. Now there is one change in sign. And what we're going to do in this talk is say that only rules 1 and 2 are accepted for what unification means. And what's great about that is it tremendously restricts the kinds of proposals you can formulate. But then you have to make connections between that formulation and the rest of physics. That's the real challenge. When we learn some more about physics, we accept the divorce of gravity from electromagnetism, and the cause is the same, which is special relativity. Because the force laws of Newton and Coulomb are rank 1 force laws in that they depend on a scalar field. But they both have the same flaw that changes must propagate instantaneously. Now when you change the perspective a little bit to field theories, the Maxwell field theory for electromagnetism is rank 1. And what Einstein did for gravity after 10 years of struggle was find a field theory for gravity that was rank 2. Now there is a toy theory, that model of general relativity, that is rank 1, but nobody takes it very seriously. After all, it's a toy. So our strategy here of just doing very small modification of players is not going to work. So we had to side with one of these more mature theories and not the other. So we want to be young in spirit, but wiser. We have to get the unification of gravity and EM and the weak force and the strong force. So if we go with gravity, we know gravity doesn't get along with quantum mechanics, and more than 80 years of efforts that direction have failed. There's no obvious connection between the weak force and gravity, and the same goes for the strong force. So gravity as a starting place does not look good. Electromagnetism gets along well with quantum mechanics. All you need to do is pick a gauge. Now the weak field theory was based on electromagnetic theory. It's just that the group underlying the theory is different. It's SU2, not U1. There's more complications and subtleties involved in that, but that's an underlying kind of link between the two. And the strong field also has some similarities to EM. It's just that we change the group. That again has very important technical ramifications, but a lot of what's done in strong field is based on EM. And so it just looks like EM has the connections to the other aspects of physics that are going on, the physics of fundamental forces of nature, and so it looks like that's the one that maybe one should go with. So you always start a field theory from the Lagrangian because that is all ways to trade energy in a volume. And what we have here is a current coupling term, which is the JA term, and you have a field strength tensor contraction. Now we've got that minus sign in there, and that means that this is an anti-symmetric tensor, so that if you switch the indices there, it will flip signs. That's actually an indication that this any force that comes out of this will have a spin 1 nature, and spin 1 particles mediate forces that repel from each other, which is also consistent with electromagnetism. And we have one set of tensors there with the indices down and the others with them up, and so they contract and form a scalar. So by the rules that we have imposed here, there really is only one possible Lagrangians to work with, and that is where we put a plus sign in there. And that now makes a symmetric tensor, rank 2 tensor, such that if we switch around the indices, it doesn't change its value at all. That's actually consistent with a force mediated by an even spin particle. So the lowest one would be like a spin 2. And for that sort of particle, like charges attract, which is certainly a property of gravity. So that's also very good. So what do you do with the Lagrangian? Well, you write it out in detail, like a good graduate student homework assignment. And you see this all here, all these terms. And what happens if you flip signs? Well, if you flip signs, then these two rows just actually also just flip signs. The rows 2 and 3, 1s and 4 and 5 kind of stay the same. So that's a nice subtle difference. There is a technical qualification which actually goes away if you rewrite this Lagrangian in a way I'm not going to go into. It gets a little bit too technical. But this is kind of the terms that make up the Lagrangian I'm going to be working with. So what do you do with the Lagrangian? Well, you can't detect a Lagrangian in nature. Instead, what you do is you take various derivatives of this Lagrangian, and that leads to, say, the energy, the momentum, the stress tensor, and also the field equations. So you can derive the field equations using the Euler-Lagrange equation. And I'm only doing this for 1 out of the 4 equations you get out of this process. But this is Gauss's law, where you have that rho and the minus del squared phi. And because those signs are actually different, that indicates that you have like charges that repel from each other. And the ones with the del 0, that's actually a time derivative. And that's very important because now changes in the electric charge density don't propagate instantly fast. They've got this time component, so this is now a relativistically invariant form of Gauss's law. So when we put those changes in the what we end up with is this proposal for gravity, and we see Newton's law where we have the same sign for both rho and the del squared phi, which is a sign that we have like charges that attract. And we have that del squared, del 0, which means that a change in the charge density does not propagate instantly fast. It's governed by the del 0 term. So this is a relativistically invariant form of Newton's law. And I had to use both italics and bold to emphasize that these del's here are not the normal derivatives. They are covariant derivatives, And covariant derivatives are the sum of the regular old derivative and the connection, where a connection is the change in a metric. So, because these have covariant derivatives, that allows for metric solutions to the field equations. But more than that being a possibility, I have found a solution. The exponential metric, in fact, is a solution to this Gauss's kind of equation. So if we assume that the potential is constant, then when we expand out the definition of the covariant derivative, the derivatives of this constant potential, of course, are zero, meaning that all the change that we measure must be due to changes in the metric. And then you apply the definition of a Christoffel symbol of the second kind, and because it's diagonal and because it is static, only one of those terms survives that kinds of process. Because you have this contraction, the exponentials actually nicely cancel each other out, and so you're basically left with this del acting on the exponential, or actually a del squared acting on the potential, and that's something that even Poisson would have recognized. So we know that's going to be consistent with observations seen in nature. How do we know that? Well, because the exponential metric actually does pass our current tests of gravity. If you measure light bending around the sun to what's known as first order ppn accuracy, it's exactly the same as the Schwarzschild metric of general relativity. If you go to the second order kind of level of tests, then this exponential metric predicts 0.8 micro arcseconds more bending than Schwarzschild. And this is really nice because back in 1919, it was Newton versus Einstein in the light bending experiment. It was a very hard experiment to do at that time, and even today we kind of question whether it was done in an honest and fair and impartial way. But it was really pushing the technology of the day, and the one that said more bending won. Here I want to do exactly the same test with exactly a millionfold more accuracy than that, and we can't get there today. The current state of the art is 100 microarcseconds, and once you get to this kind of level of precision, you have to worry about the fact that the sun turns, that there's a quadrupole moment. It's going to be really, really hard to tell this kind of subtle difference between the two proposals. That said, it still is very significant that there is a clear and unambiguous way to, at least conceptually, to tell the difference between the, Einstein's theory and this proposal, this unified field theory, that comes down to just do the experiment and whoever is right is right. That's something that people who work with strings can't say, or loop quantum gravity, or non-communicative geometry, and so that's very significant in my estimation. If we look at the precession of the perihelion of Mercury, it is again identical to general relativity. That's not surprising because that's basically a first order ppn test, and I've ground through the kind of calculation for it. Gravity waves are actually predicted to be longitudinal or scalar modes of emission. We haven't detected a gravity wave, and we certainly haven't detected a gravity wave in 6 different along 6 different axes that we would need in order to figure out what kind of mode of emission it had with a polarization. But in this proposal, the transverse waves are EM, and gravity has to be longitudinal or scalar. So that's a nice nice, at least conceptually, very clear difference between general relativity and this unified field proposal. The lowest modes of emission for gravity wave emission is going to be the quadrupole moment, because this theory is like so simple. Oftentimes what happens, like with the remote Rosen's theory, which has the same metric, by the way, it's a bimetric proposal. So there's this extra metric metric field around that can store energy and momentum, and that means that you can have a bipolar emission of gravity waves, and yet that's not consistent with what we've seen. But this theory has less, and this is one, and that's important because there's basically no other place to store energy and momentum. So all an isolated source can do is wobble like a water balloon, and that's a quadrupole moment. So I said that we had to make some kind of connection between this proposal and the weak and the strong force. And so I think that can be done at least tenuously at this time via some substitutions. What shows up in the proposal is this 4 vector. And a 4 vector you can add, subtract, and multiply by a scalar. You can't multiply it. And to get into group theory, you need multiplication. You have to be able to take these things and multiply by other members of their group. So what I'm proposing to do is take the 4 potential and write it as another type of 4 potential, which has multiplication properties, and that would be the and division properties, and it's called a quaternion. It's still a quaternion is still a 4 vector. You could still add it, subtract it, multiply it by a scalar, but you can also multiply quaternions times each other and still get a quaternion back. Now, the usual way to represent the group U1 is to take a complex number and normalize it to itself, which is what I propose to do right here. Just stick that in, and you can spot out U1 symmetry. It commutes with itself, which is all it really has to do. Now, to get the electroweak symmetry, the weak theory, actually, the SU2 group is known as the unit quaternions, and the way to one way to write that out is as the exponential of one quaternion minus its conjugate, which basically gets rid of the scalar. That's got then has 3 numbers in the quaternion. And you can then multiply that by this U1 thing that we just defined. Now, you can write that on the left or the right. It won't make any difference. In other words, this commutes with itself because they all point in the same direction. If you point in the same direction, you don't have to worry about the cross product, and that stands up rather nicely. Now to go to SU3, which has 8 elements in its algebra. My thought there was to just take 2 different kind of potentials and multiply them by each other. Now we see all the groups U1, SU2, and SU3, which are symmetries underlying the forces of nature. But this is not going to be the standard model where we think about it as U1 cross SU2 cross SU3, with some other technical qualifications thrown in there. That's got 12 elements to its kind of underlying structure. This only has 8. It's essentially trying to be smaller than the standard model. Everyone tries to make it larger, but this is the opposite direction. But compact is usually good. And all I want to do at this point is to say that we've got some kinds of insights into seeing those symmetries simply by substituting for the potential, so that this has a chance at least of having enough structure to have the weak and the strong force in there. But certainly that's a far way away from saying we've actually really made some progress there. All right, so now we're going to deal with a problem with this proposal, and it has to do with the tiny vector coupling term, and what that tells us about spin. So I've written this out explicitly. And now this scalar actually has nothing to do with spin. It's the phase of this scalar that is all about spin. Spin 1 means that like charges repel, and that is the case with EM, whereas a spin 2 kind of phase tells us that like charges attract. Now, the whole issue of spin is often kind of marketed as just impossible to get any kind of handle over. But spin is kind of done by the simplest particles out there. And I like to at least try and get a little bit of a handle on it. And so I'm actually going to look at some classical symmetries and think about them a little bit. This is just a digression. It's not important to my main thesis, but this is a system with spin 1 like symmetry because it just takes 2 pi to go around. And if you look at my wedding ring here, you'll notice that if you go just pi times around, it really ends up looking the same. And so this is kind of a classical system where we can see that you only have to go around pi times and you kind of get back to something that looks exactly like where you started. But then what happens in quantum mechanics? Well, you had to have these same kinds of symmetries going on. What you do is you end up measuring a state, and those states are incredibly clear. There's nothing fuzzy about a measurement made in quantum mechanics. It's just that you can make 1,000 of these in a row, and no one state follows another state. We just don't know what they're going to be. But with a system that's in the that has 2 pi symmetry or spin 1 symmetry, we could catch it in all these different states, and we get what the average looks like, and that's what an average duck looks like. Oddly enough, we see a concentration in the middle, and it's kind of going around all around it. And we can do a kind of similar kind of exercise on the ring. If we just go around just pi rotations, we're going around more than that isn't going to like change the story anymore. So that at least is a little bit of a handle on this issue. As I say, this perspective is not important to understanding what goes on subsequently, because it's good old Feynman who really teaches us about quantum spin, and I found what I consider to be his simplest statement about the algebra. We know that x plus or minus iy times x plus or minus iy are evidently of spin 2 and projection plus minus 2. These products are xx minus yy plus minus 2x ixy. So let's just be more pedantic and just look at the math, and we see we just multiply the plus together, and we get xx minus yy plus 2ixy, and then we do the minus case, and we get the similar thing, except that imaginary part, it nicely cancels out. And this is the sign that we're dealing with a spin projection operator. And we've got the 2 up there, and that 2 up there is important, why the states kind of project a 2 instead of some other number. They basically kind of work together, is the way I phrase it. So that is spin 2, okay? But what about spin 1? Well, spin 1, we just kind of mix around the where the pluses and minuses go. And when we do that exercise, we see that, again, the imaginary part completely disappears, as it must, because this is a projection operator. We can also spot that the values appear to be plus and minus 1 up in that imaginary kind of phase space, where we're taking x times y and getting this imaginary thingy. But that imaginary thingy is an issue. It's an issue because a vector like the current density, you just cannot do the x times y operation. because I said it was a vector. And what you can do with a vector is you can add one vector to another or subtract it. You can multiply that by a scalar. You can actually contract two vectors together, no problem. But what is clearly not allowed is multiplication. And that is what the xy is. That is multiplication. That's not a contraction. So I think what's going on is I'm going to take that implicit multiplication that he does and make it explicit by treating the currents as quaternions. And so if I evaluate this little product here, where I just change the order of the two currents, what I get is exactly the scalar that we see in the Lagrange density that I say has absolutely nothing to do with spin because it's got nothing to do with spin. And now I look at the phase part, the imaginary part, and I see my spin 1 fellow. I see that we've got these two terms. They don't work together. They cancel each other out. And so that's kind of doing the spin 1 algebra exactly as I kind of written out before. And then I look over at the spin 2 and I see something, sorry, the other terms, and it looks kind of like spin 2, but it's got a problem. And that is it doesn't disappear. Okay, and so that brings us to the observation that gravity and electromagnetism are similar but different. And now we're going to be a little bit more precise in our statements there. We have a symmetric tensor for gravity and electromagnetism, and in both cases it is rank 2. But for gravity it is symmetric, and that's important because the spin in that tensor of a particle represented by that tensor must be spin 2 because like charges attract. And in EM, that rank 2 tensor is antisymmetric, which is also necessary, just absolutely demanded, because the spin is spin 1 where like charges repel. And by looking at the current coupling term, we got the nice Lie algebra that we always hoped, and actually we kind of almost demanded for EM. But the algebra for gravity, it's not a Lie algebra. It looks like a Jordan algebra, which is like a Lie algebra. It's just got one sign change. Now, to be perfectly honest, I don't understand all of the consequences of the fact that it looks like that's a Jordan algebra that I need in order for this spin 2 kind of phase that's necessary to have like charges attract. I don't understand all the consequences of that, but that I think is a fundamental way that gravity and EM are different from each other. So what are my expectations for this talk with these professionals? Well, and it's going to be really kind of based on observations I've given to other groups of professionals, and that mostly is that people don't see it. It's very much like those color blindness tests. I really hate all those things. You know, there's a number in here, and I often cannot see it. No, it doesn't matter how much they point, and I just go along in my own merry way. But for those people with PhDs who are reading work on strings, say, and they don't see my proposal, but they've been reading stuff on strings, and they get a little frustrated with that work because, well, it looks like it's not necessarily correct or wrong, or it just looks complicated and far too complicated for the simplest things in nature to actually do. So if you do have that level of qualifications and you're very frustrated, I don't recommend going after the author of such a complicated paper because, you know, the work on strings is so complicated, and yet if it's not true, they can just make it more complicated. And if that's the case, then why fight it? I mean, they just claim it's more complicated than you understand, and you can't win that battle. So if you're that down and out and frustrated, what I would hope you would do is someday really go and attack my own work. And I say it in that kind of a way because that's really all I'm interested in, is people who take out their intellectual Louisville slugger and really try and bash this thing. I think if you do go through that exercise, like derive the field equations from the Lagrangian, I think you'll notice that it's not a trivial proposal. There's something substantial here. I've dealt with a number of the issues, but I certainly cannot expect myself to deal with all of the issues, and the reason is quite simple. If correct, or at least if in the neighborhood of being correct, then it's an intellectual structure broad enough to handle all the interactions of gravity, electromagnetism, the weak force, and the strong force, which would cover a lot of territory, particularly since there are not that many calculations that we ever teach even graduate students to do about the weak force and the strong force. So I really think there is a lot of here there, and hope to hear from you if you do give it a try and give it a test spin. And if you run into an issue, I certainly would be interested in talking with you. Thank you very much.